So the slight change of tack today is from the first talk this morning, is that I'm going to be talking about some science. I'll be talking about next generation batteries. Now, the previous speaker got a very good introduction when he was talking about sustainability of materials, in particular, the energy needed to go into making them. And this is where, and actually the abundance of those materials. So, and this is where I'm going to be starting with this talk. So we'll know about lithium ion batteries in the sense that there is a problem with supply of the raw materials. So with lithium ion batteries, you have a fairly large amount of energy per kilowatt hour required, which results in 150 to 200 kilograms of CO2 emitted per kilowatt hour battery produced. Lithium is extracted from a limited number of countries, and it's actually concentrated in the south of America. Actually, 50% in 2015 of lithium was created in just this small region here. And the rest is geographically located, but there are some places where I would say that it's difficult to get lithium from. So you have China, which is not on the best of terms with many countries in somewhere in the Middle East. You've got sub-Saharan African countries, which are somewhat politically unstable. In order to get the cathode working, you need to have cobalt, where there are also limited sources, and its extraction is environmentally damaging. You typically want to use copper as an electrode or current collector, which has high energy demands to extract. And then you want to typically use graphite as the anode, and that will be from mines or from petroleum coke, both of which will be supporting the fossil fuel industry, which I think we need to avoid at the moment. So we need more environmentally friendly batteries. What about sodium batteries? Well, sodium ions are everywhere, and they're relatively easy to extract. There isn't a shortage of cobalt because you don't need to use cobalt cathodes. Instead of using copper, you can use aluminium as a current as a current collector, which reduces the energy required. And instead of using graphite, you can use processed natural waste carbon. So in this case, I think it's coconut husks, but you can do it with many things. And as a result, sodium ion based systems have got the potential to provide energy at $23 per kilowatt hour per annum, which is less than half the cost of lithium ion batteries. So how does a battery work? Well, you charge from the cathode, which is quite often a layered oxide involving sodium or lithium, across some sort of separator into an anode, which is in this case a carbon. To discharge, you move back through this separator. It's important that the separator is a good ion conductor, but a poor electron conductor. You want your electrons to flow through the circuit and not short circuit through the battery. Otherwise, you end up with fires. Now, in terms of materials that you can use, there's quite a lot here. You'll see that the working potential of the anodes is low, the working potential of the cathodes are high, so that's how the battery works. You need a potential difference. I already said that cathodes tend to be iron oxide, sodium oxides involving sodium. They can involve cobalt, but they don't have to. There's a lot of iron compounds here and some manganese here. And then down the bottom here, there's more iron, chromium. They don't have to. You can also, in some cases, use graphite, although the potential is a bit lower. For anodes, again, you've got a large number of different anodes that are available. In this particular talk, I'm going to be talking about non-graphitic carbon down here, low working potential, but reasonable capacity, 200 to 300. Okay, if you're going to make anodes, you need to bind them together, otherwise they're just powders. So here are a list of powders. This is a number of papers from a couple of years ago. And you can see here that there's lots of different binders. I say etc. because there's a bunch of other ones that are not worth mentioning individually. And then you also have a large number of electrolytes. So in this case, you have salt, you have a solvent, and you have some additives to change the electrochemical properties or stability. So particular, what I'm going to be talking to you today is sodium electrodes from biomass, because in this case it's anodes, and we need to make our materials sustainably, our batteries sustainably. We've established that sodium in principle is better for the environment than lithium, but how do you make sustainable anode materials from waste biomass? Well, you can turn waste biomass into hard carbons that are suitable for electrodes via, you collect your biomass waste, whatever that might be. Could be coconut, could be palm leaves, could be rice husks, could just simply be a non-waste material, although that would be bad for the environment, using primary farming land to create sugars which could be eaten, but instead using them for batteries. I think that's a bad idea. You need to make it work for the waste material, so that we take waste material that is generated when we make food and then turn that into something useful. So you take your biomass, you put it into a pressure cooker. This is a high pressure vessel. I can't remember the pressure, 200 to 300 degrees C. Okay. If you harvest early, so before the reaction is completed, then you can get small molecules you can then use as feedstock for other chemical processes. Okay. If you harvest once the reaction has completed, then you get carbon dots. Now, carbon dots are of the right size to be quantum dots, such that you can, for example, use them as fluorescent tags or fluorescent nanomaterials. They're optically active, and the size of the of the quantum dot determines the color that you get. The temperature and the feedstock and the additives and the length of time that you do it, plus a few other parameters, determines the size distribution. If you take this output and you pyrolyze it at greater than 1000 degrees C, then you can get all manner of different carbon structures depending on that pyrolysis. And this can be used for electrocatalysis, heterogeneous catalysis, gas absorption, supercapacitors, or batteries, which is what we're going to be talking about here. So obviously, if you're going to be making all manner of hard carbons, you need to know what hard carbon you've got. Two techniques that you can, or one technique that you can use is small angle scattering. In this case, it's an X-ray, but it could equally be a neutron beam. The X-ray hits the sample. There are features in the sample that cause scattering. It's a bit like diffraction, but instead of it being on the small scale, it's on the bigger scale. So that's what you need, small angles. You have a large distance between the sample and the detector. And then you have a detector here that measures some kind of spectra. This spectra here tells you everything that you need to know about small angle spectra. You have an initial loss in intensity, and that corresponds to scattering from macropores or surfaces. Then you have the region that we're most interested in, which is the nanopore size, which is where the sodium ions are stored in this region here, the nanopores. And then you have atomic structure, where you're looking at structure between layers or between carbons within a ring. And here's an example of what happens when you take a material that looks like this, which is a bit all over the place. Here are your quantum dots of different sizes, which can then be harvested. And here is just some porous carbon that doesn't have a structure. So this is the output from the hydrothermal cell. And then if you heat it in a furnace under flowing gas, you can see the graphitic layers forming as a function of temperature. So as you increase the temperature, you turn this mess into something that's more graphitic. Okay. So this graphitic mess still has pores in it. You want to be thinking about how batteries work. There are still some unanswered questions with regard to battery charging, discharging in these systems. But as a general rule, you can see two distinct regions when using these materials as anodes. Now, the cell geometry we typically use are half cells. That means that you have an anode, a separator, and then just some sodium metal, because it makes life a little bit easier when you're looking at the anodes. So you can see that there's a sloping region and a plateau region. There's a sloping region here and a plateau region. Okay. So it is thought the sloping region is due to insertion between nearly parallel graphene, so in this region here. Okay. It's thought the plateau region is attributed to either sodium intercalation between the expanded graphene layers or into these nanopores here. Okay, that is what's thought. In fact, you can see a beautiful diagram here. The blue ones correspond to the blue, the red ones correspond to the red. So let's think a little bit more about structural characterization, because battery capacity is definitely a function of structure. So we take our biomass, we put it into a pressure vessel, we heat it. We then put it into a beam, either of neutron scattering or X-ray scattering. X-rays have got a Q range that stops about here. Neutrons get extended out here. Now here is an example of what happens when you put in a pristine material and you put in something that's been heated to 1000 degrees C. You can see immediately that not very much is happening down here. Now this is scattering intensity normalized versus the despacing distance. Down here, there is hardly anything happening. Basically, not much is happening to the graphite. Out here, you can see that the black one, which is 1000 degrees C annealed, there is something happening. There is an additional peak there. This corresponds to nanometer-sized pores. There is a distribution of nanometer-sized pores when you heat it. Now, looking into this in some detail, it gets complicated. So you can see when you look at the precursor, I said there wasn't very much going on at low temperatures. Well, there is actually. There is something going on. So if you go from, actually, this was probably, okay, it doesn't matter. So if you go from precursor to 1000 degrees to 1300 degrees, you can see this bump developing. You can also see, actually, there is a small change down at low D. You get an additional peak forming there. Okay. If you plot the ratio of D2 and D1, D2 and D1, D1 being the direct CC bond distance, D2 being the next nearest neighbor CCC distance, you can see it increases. So there are more next nearest neighbor carbons in the sample once you increase the temperature. D3 corresponds to the carbon ring diameter, this peak that appears as you increase the temperature. That also increases. So if you plot the peak ratio D3 over D1, you can see here that you get more aromatic rings. Now, if you go between the precursor state or just before it to the precursor state to 1500 degrees C, you can see quite a significant increase in the overall amplitude of this peak. But then if you go from there to 1700s, you can see that there isn't an overall amplitude change in this region, but there is here a reduction in amplitude, which suggests that the pores are becoming more ordered. It suggests that the pore distribution size is becoming smaller. So how does that affect the function of the material? So we've got a measure of pore diameter as a function of temperature as well. You can fit the data and you can extract pore diameter as a function of temperature. You can also extract the domain, or not the domain size, you can also extract the distance between these two graphitic layers. And you can see that the pore size increases, but at the same time, the layer spacing decreases to the graphitic level. And also you've got DO2O, which is another graphite length scale, which increases to the graphitic values. And now if you look at binding energy, okay, let's not talk about that. Now if you look at specific capacity versus potential, you'll see that you peak at about, your peak capacity is 1300. So it's like you don't want graphitic domains, but you do want to have slightly higher pores. Okay, so there's a balance between pore size and domain size that you need to do. And as soon as you get to above 1500 degrees C, this drops off. Okay. So I think the take-home message there was you want to minimize ions, sodium ions going into the graphitic structures and maximize sodium ions going into the pores. So now we're going to be talking a little bit about muons, which is another technique. Here's a picture of a spectrometer. You can see lots of detectors around in a circle there. There are some detectors behind in the second ring, if you see there. Okay. So here you implant a fundamental particle. It's related to an electron. It's in the same family as electron. It has it is a fundamentally it's a fundamental probe of spin dynamics in materials. Now sodium has a nuclear spin, so muons are therefore sensitive to it. Now they are 100% spin polarized at production, and so and you're able to measure the evolution of the muon's spin in the sample by putting these detectors around it. These detectors actually detect positrons that decay from the muon as a function of time. So it's just a radioactive decay from a muon into a positron, which are then subsequently detected. Okay. So you put your sample in the beam, you have a small degrader on there to make sure the beam's sitting in the right place, and then you put detectors around your sample. You monitor the muon's spin as a function of time, which then gives you a measure of the spin environment as a function of time. And here are some examples of the data that you can get from it. You can see here that if you imagine that you have a sodium spin in the sample that is not diffusing, then it's going to have an effect on the muon spin because it's a static coupling between the one spin and another spin. If you have sodium spins that are moving past the muon, at some point they decouple so that the sodium is moving too fast to be able to effectively couple to the muon. And that's what you see here. At 50 Kelvin, you have this 100% spin polarization or 20% asymmetry, which remains almost unperturbed at 400 Kelvin. There's very little relaxation as a result of sodium's moving and not coupling to the muon. At low temperatures, you can see that there is a loss of this amplitude of the precession. And that loss of the amplitude is because at this point the sodium is static and it couples to the muon spin and simply dephases it. So if you measure, therefore, this dephasing rate, this relaxation rate as a function of temperature, you can extract the hopping rate of the sodium as a function of temperature, which is for a sodiated sample and for a desodiated sample. And you can see immediately that the onset is slightly lower here than it is here. And you can also see that as a result, the activation energy is 88 millielectron volts for the sodiated sample compared to 152 millielectron volts for the desodiated sample. So it is well known that sodium gets trapped in these materials. Okay. What happens is you lose your initial, if I go back here, I think here, you can see here there is an initial capacity and then you lose some. An initial capacity and then you lose some. And for some reason, this is reversed and I haven't worked that out. But out here, which is where we measure, there's an initial capacity and then you lose some. So if you sodiate it, you have an initial charge. You then desodiate it, you remove that charge. Some sodium gets left behind. Now, and that's the reason why you have lost that initial capacity. You get stuck. Turns out that that sodium that's left behind is still there, can still couple to the muon, and is still mobile. Okay. So DFT calculations for sodiated material says that the activation energy should be 100 millielectron volts, which is about right. That's what we get. We get 18 to 88 plus minus 13 millielectron volts. So our DFT calculations were for along a single sheet. However, DFT calculations for 2 graphene sheets, say 180 millielectron volts, which isn't so far from here. But long distance migration is blocked in this mechanism. In other words, the sodium cannot escape 2 sheets. So what that means is that if the sodium goes in to a pore, that's a single sheet of graphene because there's nothing out here to stop it. And it can get in and out easily enough. Whereas if a sodium goes into 2 sheets, between 2 sheets, it gets stuck. That's what the DFT calculations say. And that is manifested itself here in our desodiated data. It's still there, it's still mobile, it's just that it can't escape the sheet on the macroscopic level. And if you remember, the capacity peaked at a point at which graphene sheets began to come in. So if you have too many graphitic features, they get too close together, then you have a higher blocking mechanism to get desodiated quickly. Okay, so now if I have the time, this is some new data where we're looking at solid electrolyte interface formation in mesoporous carbons. So it's the same idea. You take
4 minutes. Okay.
Okay, so it's the same idea that you take a short, you take molecules, you cook them, you create structures, you pyrolyze them. If you might even be able to template them to create additional features. Okay, so we've done X-ray scattering, we've looked at relative pore capacity. Here's a beautiful picture of what we have out. Look at these beautiful spheres over a large length scale. Okay, I'm not going to spend too long on this. Here is our rate, potential versus specific capacity. 1500 degrees C appears to be the best temperature to run this system out, and that's because the pores are bigger. Okay. You can see here that the slope region contributes the most until you get to 1500 degrees C, when the plateau region just about contributes to the capacity. Now, the interesting thing is, this is where I'm going to be talking about, we're looking at solid electrode interfaces. So if we look at the first cycle capacity of the sodium PF6 salt, we've done 3 different salts: sodium PF6 in a dig lime, sodium PF6 in ECDMC, and sodium chloride in ECDMC. Okay, so you can see here that the sodium PF6 salt is higher in ECDMC than it is in the dig lime. And actually, that you have good, however, the dig lime has got better capacity retention after 200 cycles compared to the DMC. Okay. And I think that the lower initial dig lime capacity comes, compared with the ECDMC, comes from the solvent co-intercalation within the graphitic layers. For the sodium chloride system, chlorate system, the highest first cycle capacity is present, but it has the worst long-term cyclability. Okay. If you look at the impedance spectra, again looking at the dig lime, there's a flattened semicircle, so there's no semicircle here. Okay. This suggests that there's a stable conductive solid electrode interface. The fact that here you go from you retain 70% of the capacity also suggests that you've got a stable SEI that's protecting the anode. Okay. However, these two have got a higher overall resistance. Okay. This increases with cycling, which suggests that the SEI is becoming more resistive in these systems. Now, look, if you look at the XPS data, if you look at the sodium cobalt cobalt oxide and the C double bond O, these are derived from essentially oxidative decomposition and polyester derived from the solvent, and they are relatively weak in the dig lime system, all the way down here, and relatively weak down here compared to the other. And you can see here that in the sodium fluoride bond comes up, suggesting that actually it's distributed, that the sodium carbonate is distributed on the top surface in this system here. Okay, so there is a warning that when you do etching, so the idea here is that you can bury down and look at the different layers in the battery by etching. When you etch, you can introduce oxygen containing functionalities, which is a problem. So we did some DFT of the anion fragmentation as in the different systems, and we can see that there's a stepwise oxygen loss and the oxygen can easily attach itself
Buka suara.
to. Okay, 2 more minutes because I started late. We can see that the oxygen can easily incorporate onto the basal plane. We can also see that fluorine fragments are also successfully detached, and that when the carbon is fluorinated, you see this additional puckering here. Okay, so the presence of chlorine, fluorine, oxygen close or bound to the carbon surface could be beneficial for the initial sodiation storage, but it also leads to the irreversible entrapment of sodium ions and capacity loss. Here is a schematic diagram of what's going on with when you combine all of the data that we have. Is that when you have a sodium PF6 diglone combination, there is a thin and homogeneous layer of sodium fluoride formed. And this serves as a conductive barrier, but protective layer, which means that that's why you have high stability. If you look at the sodium PF6 ECDMC, then you have you do have a formation of a protective layer, but because the solvation of sodium is worse, you get organic compounds derived from the electrochemical decomposition, which increases the interfacial resistance and then in turn lowers the long-term stability of the anode. And you end up with sodium cobalt oxide. And then finally, in the chlorinated salt, you actually have decomposition of ClO4 minus, which then enables the functionalization of the carbon, and you end up creating sodium chloride layer. And a sodium chloride layer is reactive and not protective, and you end up with a premature failure of the cell. So I won't go through the future, and I think I will just say thank you to the team who have done all of this wonderful work. And like I say, I did start late, so it's now, yeah, okay, almost